Okay, welcome to section 2 of the course, working with subnets, availability zones, regions, and serverless. We're going to talk about understanding subnets, availability zones, and regions, and we're going to define these components within AWS in terms of high availability and secure control. So regions, availability zones, and subnets. So as you recall, we left off with the end of section 1 where we had built this architecture. We built in our lab this one region of this larger proposed architecture where we had 2 availability zones, we had a load balancer, we had an auto scaling group, and we had EC2 instances in our public subnet, and we had a private subnet with another EC2 instance in it. And so we did a kind of quick run through of building out this environment, but we didn't go into the details of how regions, availability zones, and subnets work together to give you the high availability, elasticity, and power of the AWS cloud environment. So we're going to drill into those subjects in this section of the course and specifically in this video. So regions and availability zones, how are they defined? So AWS Global infrastructure is built around regions and availability zones. And AWS has regions all across the globe and availability zones of at least 2 in every region. Many regions have 3 or even 6 availability zones. So regions are defined as such. Each region is a separate geographic area where cloud resources can be instantiated. So we have the US East 1 region, which is in Virginia. We have the US East 2 in Ohio, US West 1 in California, US West 2 in Oregon, and so on, all over the planet. And within each of those, we have availability zones. So regions are isolated from each other and are designed to be autonomous. So if it ever happened that an entire region was affected by a natural disaster or something like that, that region could go down and all other regions around the globe would not be affected. They are completely isolated. Availability zones. So each region has multiple availability zones, as I said, and these availability zones are physically separated and independent, just as the regions are. And they're built with highly redundant networking. So in this example I show here, we have a region with 3 availability zones, 1, 2, 3, and they are connected via high-speed redundant networking. And each availability zone is a collection of 1 or more data centers which form a campus. So an availability zone is not just a couple of servers in a building, it's actually at least one entire data center, but most are multiple data centers forming a campus. And each availability zone has independent physical infrastructure. So availability zone 1 is on a different electrical grid than availability zone 2, and same for availability zone 3. They are on different floodplains, so if any natural disaster or electrical outage happens in one zone, it won't impact the others. So with that structure of availability zones and regions, you can build what are called self-healing stateless applications. So I'll give you an example. You can use availability zones, elastic load balancing, and auto scaling to build these self-healing applications. And I have an example here. So here we have the AWS cloud. We're in the US East 1 region. We have 2 availability zones, East 1A, East 1B, and we've got 3 subnets. One is a web server subnet, another is an application subnet, and the third is a database. And you can see we have auto scaling groups for both web and application. So what we do is we monitor and recover from common failures in this infrastructure by decoupling application interdependencies and removing states from our application components. And we use queuing, load balancing, auto scaling in the application architecture, and elastic load balancing decouples the client from the servers. And auto scaling gives us this capability that if a server fails, the client connection can be rerouted to another working server. So here we have this server failed, auto scaling produced another working server, and the load balancer working together with auto scaling rerouted traffic that was once going to the failed server now to the new server. So these application components need to be stateless because if an application server fails and we reroute client traffic that was once going to that server to a new server, can't be saving state within the server because that state won't transition to the new server. So in order to take advantage of this, you need to build your applications as stateless applications. So regions and availability zones can also be used for distributed resilience. Using the well-architected framework active-active pattern, you can build this model where you have the AWS cloud, you've got 2 regions, US East 1, US West 1, and we've got the same structures we had in the previous slide, but this time we're using bidirectional replication between our two master database servers, and our secondary database servers are being replicated to by their masters. So how do we use this? Both application stacks are used simultaneously to serve production load. So you can see Route 53 is routing 50% of the traffic to one region and 50% to the other. And they keep each other in sync by having bidirectional replication between their master databases. And Route 53 is splitting that traffic 50-50. So when Route 53 detects a failure of the application in one of these regions, it'll automatically direct 100% of the traffic to the surviving site or surviving region. And so both stacks are being used actively. Data replication, as I said, needs to be done in bidirectional mode so that we can keep all of the data serving these application loads consistent and in sync. So that's an example of using regions and availability zones together with load balancers and auto scaling to produce a very resilient, elastic, highly available application infrastructure. So VPCs within regions and availability zones. Let's now drill down to VPCs and subnets within this structure. So your VPC spans all availability zones in your selected region, if you define it that way. And here's an example of that. We have the region, we have a VPC spanning availability zones A, B, and C, and it has a routing table to help route traffic across those availability zones. We'll get into more detail here in a second. So subnets. We add subnets to each availability zone. Just for this example, we're showing a VPC within one availability zone to keep it simple, even though this diagram is hardly simple. But I want to show you how you can use subnets to define traffic and create an elastic, resilient environment within your VPC. So we have a VPC with a size of 16 IPv4 CIDR block, which provides us with 65,536 private IPv4 addresses. So this is our VPC with a CIDR block of 10.0.0.16. Add to that an internet gateway, which connects to the internet and to other AWS services. Here's your internet gateway being accessed by the internet. And we have a public subnet with a size of 24, 10.0.0.0.24, which gives us a CIDR block of 256 private IPv4 addresses. Even though it's a public subnet, the IP addresses within it are private. And you can see here we have 10.0.0.5, 6, and 7 within our public subnet. And associated with this public subnet is a route table that has a route to the internet gateway. So you can see here the route table used by the public subnet has a target for when any device in here tries to go to the zeros destination, will be routed to the internet gateway and allowed out to the internet because it's a public subnet. We have a NAT gateway in that public subnet, which instances within the private subnet used to get out to the internet to retrieve updates for those servers. So you can see these database servers in this private subnet, they have a route table of zeros going to the NAT gateway. So they route through the router to the NAT gateway, and then from the NAT gateway, they can go out to the internet. Our private subnet, which is also a subnet of 24 CIDR mask, gives us another 256 private IPv4 addresses. And you can see we're using 10.0.1.0 for that subnet. So it's a different subnet mask. And that set of addresses within that subnet, private addresses for these database servers, 10.0.1.5, 6, and 7, they are going to use their own routing table to get access to the NAT gateway. So when these servers try to go to the destination of zeros, they'll be routed to the NAT gateway through their routing table. That will allow them to retrieve updates to these servers within their private subnet. So this is how subnets work. And also we have here elastic IP addresses for our instances in our public subnet so that they can be accessed from outside the VPC through the internet. And they can route out to the internet and back. So what we've just covered is summarized by AWS in their 6 design principles for operational excellence. So let's go over those. We've seen much of this in our labs and in our presentations up to this point. So number 1, perform operations as code. We definitely have done this in our cloud development kit work, and we'll continue to do this throughout the course. So what you want to do is apply the same engineering discipline used for application code to your entire environment. Number 2, you want to have annotated documentation. We've also done this in our cloud development kit code where we self-document within there. So you automate the creation of annotated documentation after every build. Number 3, you want to make frequent, small, reversible changes, not only in your code, but also in your environment code, as we've seen in our Cloud Development Kit examples. Number 4, refine operations procedures frequently. As workload evolves, evolve your procedures. Number 5, anticipate failure. And we saw examples of that in our resilient architectures in this video. You want to identify potential sources of failure so that they can be removed or mitigated. You assume, as Werner Vogel says, that everything fails all the time and plan for it. And then number 6, learn from operational failures. Drive improvement through lessons learned from all operational events and failures. Okay, so that's our drill down into regions, availability zones, subnets, and the idea of highly resilient, self-healing, elastic infrastructure.